I'm gonna go over number 9 in this video. This is from, well, really chapter 2, from multiple sections. And you also did this one on your exam too. I remember that one was when the population doubled every certain number of years. But this one, the population of Sunstown triples every 16 years. And A through E, I think I got part of this problem on the textbook. I think it started with like B, but I will go ahead and type up, add an information there for me. Initial population equals 4,000 in 2017. So we'll just start from 2017, and although I gave that information over here in part C, I really should give that to you in the beginning, right? So I'll make sure to do that on the final exam. Actually added part, I think what? Would like to access the microphone. Okay, access it. What am I doing? I don't need this. I'm already recording. You can delete recordings here. I don't know what I'm doing, but I think my screen recorder is working, so that's okay. All right, so A, find an exponential function of the form P of t equals P naught times n raised to the t over 16th power that models Sunstown's population after t years. And t is 0 in 2017. I really should give that information up in the problem. But let's go ahead and write it. P of t equals, P naught stands for initial population. So that's going to be 4,000 times, what about n? What about n? N in this case is going to be 3. N is 3 because the population what's the keyword? Triples. Okay. So if it was 4 for the exam 2 problem, I think it was doubles and n was 2. If it quadruples, then you'll do what? 4, but I'll probably keep it to like double or triple on your exam. Now t is the number of years, but we have to divide this by 16. Why? Because it takes 16 years to triple. So for example, in 16 years, it will triple once, right? In, well, 32 years, in 32 years, which is, well, 32 years is 32. 32 divided by 16 is 2, so it will triple 2 times. So something like that. So just a quick population. So if t is 0, and I'm doing a little extra work. When t is 0, population is 4,000, right? When t is 16, well, that's the first 16 years, it's going to triple. So 4,000 will triple into 12,000, right? 12,000. And then in another 16 years, which is going to be after 32 years, that 12,000 will triple into 36,000, right? So by just using this tripling idea, I can figure out the number of the population of Sunstown in 16-year period. I can go and do the other one. And, the next number will be just 32 plus 16 ... But as you know, population will not wait every 16 years to triple. You're not going to have like no growth and all of a sudden year 16 everybody is like tripled. So it makes so much more sense to go with what model? The continuous yearly growth model, a continuous rate. So for the continuous, that's when we bring in the base E, right? So B, find R, the continuous yearly growth rate. Now, I can do this in a little bit more, well, I'll do it the long way first, but then I'll also show you how you can just get this right, okay? So what we are trying to do is this. We're trying to convert this P of t equals 4,000 times 3 to the t over 16th power into P of t equals 4,000 times what? E to the RT power, right? If we can do that, and that's really the answer for C, that's the answer for C. That's the exponential function that models Sunstown's population using the continuous growth model. But if I solve for R here, I should be able to answer. That's going to be the continuous yearly growth rate for part B. So how did we do this? Here was the key. We're going to start with P of t equals 4,000 times, but we want the base to be E, right? So what we're going to do is we're going to rewrite 3 as E to the ln3 power. Now you know they're the same thing, right? So we can do that, and that's the little trick that we use. ln3, and then the original power is going to just get multiplied by this new exponent of ln3 t over, oh not 3, sorry, t over 16. And now all I need to do is just simplify this. So this equals 4,000 times e to the. I want to convert this in a form so that I can clearly see what r is and what t is. Notice that I can pull out or write down ln3, natural log of 3, divided by 16. Natural log of 3 divided by 16. And then multiply that by t. So here it is. This is our r. This is r. Rate is natural log of 3 divided by 16, which is approximately, now how did they want us to round this? No rounding. You know, guys, when I'm typing up your exam, the actual exam, I'll try to be very descriptive of what I want. I'll say round this to the nearest blah, blah, blah. Well, I'm just going to go ahead and round this to the nearest thousandth. All right, what's that? Natural log of 3 divided by 16. And that equals approximately 0.0. You know what? I'm going to go ahead and write it as 6866. So that if I convert this into a percent, and this is the same thing as 6.866%. Now, that will be the longer way of doing it. That is how we actually do it. But I think you know the formula for doubling. You know the doubling, what was it called? Doubling time formula? Is that what we called it? We kind of solved an equation once, and then we said, hey, this is the doubling rate or half-life. We solved for one of these. So if you take a look at this very carefully, the rate is going to be natural log of 3, guess where that came from, because this population triples, divided by however many years it will take for this population to triple. This is very similar to how we found the I mean, we did something similar. I'm sure we did. What's that? Oh, I was working on another class. Let me see if I can try to find that note for you, because it may be helpful to see more than one note. But when did we do this example? You're like, I don't remember doing this. This is when we first kind of went online, guys. And it was an application problem from chapter 2. Oh, look how far we go back. Here it is. It's under week 9. Week 9, back March 16th through March 22nd. It was the application problem page. Here it is. The population of Neelam doubles in every size. So this is the problem. And if you want to look at the notes on 2.6 application problem, and this is the same thing. But back then, well, this population of Neelam was doubling every 5 years. So take a look at this formula. To find the rate, I ended up doing natural log of 2 divided by 5. It was natural log of 2 because this population doubled. And I was dividing by 5 because it took 5 years for this population to double. Now, it's I want you to be able to come up with, and if you do that, if you skip this much work and still just tell me that rate is this, I think that's good. Instead of don't just give me that and say that's my rate, but you got to tell me how you got it. But that's the rate. We found the rate. The rate is 6.866%. And in fact, we actually found the equation too. So let's go ahead and write down the equation for part C. The continuous growth function is going to be P of T equals 4,000 times e to the 0.06866 times t. Now, this makes more sense than what we found on A, because this one, we can plug in any number in t, and that t doesn't have to be a 16-year interval, right? Okay, so we found C. Let's go ahead and use it. D, estimate the Sunstown's population in 2024. So in 2024, let me go ahead and at least talk about how I'm doing D now. In 2024, T value is equal to, what's T? 2024 minus, what was our initial year? 2017. 2017. Is that just 7 years, right? So T is equal to 7. So if I want to find the population in 2024, I got my function. I can plug in 7 into my continuous growth function. 4,000 times e to the 0.06866 times 7. All right, we're talking about population, so I'm just going to go ahead and round this to the nearest whole number, okay? So let me type this in my calculator. 4,000 times e to the, and you type this in too, 0.06866 times 7. What did you get? I got 64. Hold on, was it really only 6,000? Oh, okay. That's all right. 64, 68 people. Okay. And now I was thinking this number was way too small, because remember when we were looking at like the table, I said 12,000 and 36,000, but those were 16 years from 2017 and 32 years from 2017, so those values came out a little bit bigger, right? But it was just after 7 years, so it grew to be 64, 68 people. Okay, now what about E? Estimate the rate of change of Sunstown's population in 2024. Now you gotta remember, there's an easy way to do this. Like, this is an exponential function, right? And exponential functions are the special guys where we can write the derivative as a constant. We can do that, but what I'm gonna do is, because I want to kind of review finding the derivative of a exponential function with base other than e, I'm going to take the derivative of the equation that I wrote in A and plug in 7 in there. And I want you to do that on your exam too. All right, and I will show you another way. But if you figure out the other way and try that, I guess that's also okay. E, I'm going to find P prime of T and then plug in T equals 7. And why is it 7? Because we're still talking about 2024. So remember, P of T was 4,000 times, and I'm doing the original P of T that we found in part A. But if you decide to use the equation that we found in part C and do it, I'm not going to take points off. The answer may be a little bit different, but I think that's still very good if you want to do that. That's okay. In fact, I'll do that in this video. Yeah, why don't we do that and just kind of look at the difference? Why not? All right, so let's find P prime of T. Other way are fine on your exam. So that will be 4,000 times what? How do you take the derivative of this mess? 3 to the T over 16th power. And that's going to be natural log of 3. right? Natural log of the base times the original equation, 3 to the t over 16th power, and we must multiply this by the derivative of the exponent, right? So some crazy rules from a while ago coming back to you. So it's going to be 4,000 times natural log of 3 times 3 to the t over 16th power times derivative of t over 16 is going to be just 1 over 16. Okay? Now, we can simplify this a little bit if you want to. We can write this as, let me just put all the constants together. That's a constant. This is a constant, this is a constant, this is a constant. So I'll write this as 4,000 natural log of 3 over 16 times 3 to the t over 16th power. Now we're ready to plug in 7. Then p prime of t is equal to, p prime of 7 is equal to 4,000 over 4,000 times natural log of 3 divided by 16 times 3 to the 7 over 16th power. Approximately, let me go grab my calculator and type this in, okay? 4,000, let me put this in a fraction format. 4,000 times natural log of 3 divided by 16, and that's the constant, times 3 raised to the 7 over 16th power. Now, what did you guys get? I got 444 people per year. We just found the rate of change. So the unit should be people per year here. Now, I think that's the answer that I typed up when I grabbed this problem from from the textbook. So let me double check. I'm out of room. I wanted to kind of do another way using C and show you how close the answer will be. But I got 444. It's easy to remember. Where am I? That was the last one, right? Yeah, here it is. So, yep, they're all the same. So if you're fine with that method, stay with that method. If you want to see, because I don't mind if you take the derivative of the equation that we found in part C, this guy right here, and you can take the derivative of that one, and that's actually going to be easier. So why not? I mean, I didn't teach a class today, so I have time to kind of add another one. Guys, this is exam week for me right now, so add a page. I have time to go over. Come on, where's the page? Oh, I've been adding pages to the bottom of this. Oh, no, that's not what I want. Add a page. Okay, so why not? Let me use another equation. Let me use P of t from part C. And that should be almost the same thing, 444 people per year, but I just kind of want to show you that one. I think it's easier to work with. 4,000 times e to the, that decimal, 0.06886t, right? So if I take the derivative of this, that's going to be 4,000 times, bring down the constant, well, itself first, I'll do that first, 0.6886t. And then you multiply this by the derivative of the exponent, right? And this is the chain rule. So you know that's going to be 4,000 times e to the 0.06886t times that decimal of 0.06886. So all you need to do is just multiply that 4,000 by 0.06886. So 6886 Then you will get 275.44 e to the 0.06886t. Then you can plug in what number? Then find p prime of 7, okay? P prime of 7 equals 275.44 times e to the 0.06886 times 7. And that's going to be approximately, I'm typing this in now, e to the 0.06886 times 7, approximately 446 people. Oh, not people per year. And, well, they're a little different, right? There's like 2 people difference because, well, this model that we use, I mean, it was all, again, rounded, right? Kind of rounded. The rate was rounded, and maybe that may be just it. But they are slightly different models, right? This one that we just did were assuming continuous growth, which sounds better. But if I use the equation that we originally wrote in A, 444 is not a bad answer at all either. So you do one of them, up to you. Whichever one you find to be easier, okay? And let me remind you something. Do me a favor. This number that you got, that's the number from that's the number of people in 2024, right? And what's the rate? Rate was 0.06866. Would you multiply those for me? Let's try something, okay? How about, oopsie. You find P of t times the rate. At t equals 7. P of 7 times the rate of 0.06886 is, how many people there were? 6468. 6468 times 0.06886. Just kind of wanted to do this with you because we talked about how these exponential functions are actually very special. 6468 times 0.06886. What did you guys get? Approximately 445 people per year, right? People per year. Notice that number is very, very close too. Because this is a type of equation, we can write it as where, what was the variable? dp over dt, the derivative is equal to the rate, 0.06886 times, did we just say t? I can't remember how we wrote it, but remember one of those functions. Yeah, why don't we look it up? I may be spending longer time than I really should on these problems, but just kind of wanted to connect everything that we talked about, guys, right? They're all connected. I think it was around 4.4-ish. Oh, I hope I'm right. No, it wasn't 4.4. It was before spring break. It was before spring break when you and I were in a classroom together. Thank goodness everything is super organized. But my iPad is almost dying. So if it dies, I'll stop. But if you got all the answers about 15 minutes ago, so you can leave me, but I'm just trying to remember how exactly we wrote it. So it wasn't a week. I'm going back in time. When did we do these? Not 2.6. How about 2.5? Oh, guys, I think I'm giving up. I just wanted to show you. Maybe this one? Oh, no, that's another video of me talking. Did I put like a completed note somewhere? Oh, forget it. Forget it. You got the answer 15 minutes ago already. So, just kind of wanted to show you different ways of doing it, but I really prefer if you can show me what I did first, like taking the derivative of a logarithmic exponential function that has a base other than e. So working with the equation that we wrote on A, but if you go with the continuous growth model or this little trick that we did, I mean, you should get something very similar. But I think the notation kind of confused. Ah, okay. Yeah, but 3 different ways that I just kind of showed you to answer part E. But if you want to see another example, check out 2.6 application problem on the population of Neelam, okay? Or I'll be back with example number, I think 8 was another one that I got an email about. I'll